My name is Valli. I'm currently a PhD student at U of T, and I worked as a part-time applied machine learning intern here at Vector since January, working on AI engineering initiatives at the intersection of health. More specifically, I'll be talking about today working on my work detecting and remediating malignant data distribution shifts in clinical data. So clinical data is subject to a lot of different types of data shifts due to changes in things like technology, demographics, and behavior. Electronic health record clinical data in particular differs a lot from other data domains, as well as compared to other data modalities like imaging data. And so it's really important to establish the efficacy of drift detection methods and develop retraining strategies for clinical AI systems so that when they are malfunctioning, we know about it and then we can take action. And so model performance is obviously really useful, but it doesn't provide explanations as to why a models or why the performance deteriorated. It also requires labels, and in the context of the clinic, labels can be really expensive. And so it would also be valuable to know if drift occurred in the form of a warning at the time a model provides predictions prior to having these ground truth labels in order to influence real-time clinical care and prevent system malfunctions and poor decision-making, in addition to informing retraining. And so this is kind of the architecture of the drift module that I've been working on. And it broadly follows this schematic where we have a model that's built on some sort of source data. And then we have a rolling window with different streams of target data coming, and we're detecting drift between the source and the target data, first by performing dimensionality reduction, and then using a two-sample statistical test or a classifier method. And then once we have the drift p-value, we can actually, when it falls below a certain threshold, we can say, we want to trigger retraining and retrain our model at that point. And so right now, the module supports the following dimensionality reduction procedures, as well as two-sample tests and classifier methods. For the rolling window, you can adjust parameters like the statistical window, the stride length, the look-ahead window, the number of patients you want to perform the test on, and the actual drift threshold. You can also input your own model to evaluate and monitor across real-life events, so monitoring drift across different hospitals, which is really common, or hospital types, season, events like COVID-19, and variables like age and sex, which have been known to cause dataset shift, as well as synthetic experiments where you can induce synthetic noise and then evaluate a model's robustness to that noise. And so the data I'm using to conduct some of these experiments to showcase the drift detection module is the GEMINI data. So you heard Kaden just speak about Cyclops and the pre-processing for GEMINI that I'm not going to go over because he obviously went pretty in depth on that. But essentially, we're using electronic health record data from the general internal medicine ward from hospitals in Toronto from 2015 to 2020. The data was extracted, imputed, aggregated, and you have these patient profiles for each patient, which has different types of data modalities like interventions, imaging, transfusions, and lab data. So in the first use case I worked on was the in-hospital mortality prediction, and the goal was to build a ML model to predict whether a given patient will experience in-hospital mortality using the first 7 days of their general internal medicine stay. And so to evaluate the effects of distributional shifts on the model, I performed experiments using a gradient boosted tree, and in particular trained that on the source data and evaluated the performance on both in distribution as well as out of distribution data. So the experiments consisted of events like COVID, as I mentioned, seasonal and hospital type, and it can be seen across the in-hospital mortality prediction. It generalizes pretty well across COVID and seasons, but when you look at different hospital types, that's where you start to see, especially when it's a model that's trained on community hospitals, that's evaluated on academic hospitals that it's never seen before, it is subject to a loss in AURC and AUPRC. So we want to evaluate this in a label agnostic manner, and we want to know if there's data shift without waiting till that event occurs. And so I used the drift detection module using a black box shift estimator, which was an untrained feed-forward neural network, and the MMD test to evaluate between the in-distribution data, which is in blue, and the out-of-distribution data, which is in red, whether or not there is drift that occurred without using the labels. And that's what you're seeing on the left-hand side. And we're seeing that at even really low sample sizes, that drift is detected in the out-of-distribution data versus the in-distribution data never goes below the p-value threshold. And then when we look at performance on the right-hand side, we can see that there is a difference in performance from low to high sample sizes between the baseline and the actual out-of-distribution data. And you can also look at the features that change in the between the source and the target data using SHAP values. And so things like triage level and age are features that change in importance between the out-of-distribution and in-distribution data. In the second use case, I looked at mortality decompensation prediction. So I was building in a machine learning model to predict whether patients' health deteriorate and result in a hospital mortality within the next 2 weeks. And this prediction was done every 24 hours of their stay in the general internal medicine ward. And so trained a LSTM model from patients admitted from the general internal medicine clinics from 2015 to 2018. So only a subset of the data. And the model achieved, you can see an AURC of 0.793 and AUPRC of 0.68. And so in a simulated deployment monitoring setup, I wanted to evaluate, now we've trained a model on 2015 to 2018 data, now looking from 2019 to 2020, are we able to detect drift? And so in this setup, I use a window length of 30 days and evaluate drift between that 30-day window and data drawn from the same distribution the model was trained on. And the drift test is performed using again, the black box shift estimator and the 2-sample testing. At the top, we're seeing the drift metrics, and at the bottom, we're seeing the performance metrics. And so you can see that where it's red is when drift was detected, and at the dotted line indicates when Toronto actually entered or Ontario entered a province-wide lockdown due to the pandemic, and we actually detect drift prior to that. And that's also reflected in the model performance, which you can see through the AUPRC and the sensitivity and positive predictive value, but not as apparent in the AURC. And so when we lower the number of patients we're using for this, the statistical testing, we're actually seeing a lower sensitivity. So it is important how many patients are being used or how many data points are being used in the drift detection. So what did we learn about drift detection so far? We learned that the number of patients admissions affects how sensitive the drift detection is in both the static and temporal model setting, and it depends on the intensity of the drift. That there's an importance in the selection of metrics to be used to evaluate drift, and that drift can result in extreme decreased or improved model performance. So the next step was the retraining. And so I looked at 2 strategies so far, the cumulative retraining strategy, which is where you're basically retraining with all the data up until that point. And the most recent is where you have a window size, and the window size is adjustable, and you can basically retrain using a specific window of the most recent X amount of samples or patients. And the parameters that I played around with for some experiments were, again, the window size, the number of epochs, and the actual drift threshold to trigger the retraining. So what I found was that a larger look back window for updating results in less drift and improved sensitivity, but that plateaus. So when we're using all of the data, which is indicated by the cumulative, it doesn't actually have an improvement over using just the most recent 120 days. And so in a lot of situations, you don't actually need to use all of the data, which is really useful to know because, it takes longer to update and retrain on the entire data set. The number of epochs is associated with a higher positive predictive value, but lower sensitivity. And we found that the higher the drift threshold, there's a higher positive predictive value, but then there's lower sensitivity. So it is really about balancing that trade-off. And so what I'm working on now is wrapping up and doing a public release for the drift detection module, and a paper that we're working on for detecting and remediating malignant data distribution shifts in clinical data. And I realize this is a short presentation, so if you do want to learn more, I've had the really great opportunity from Deval, Ilham, everyone, the team, to actually present at MLOps World and MLHC 22 with Amrit. And so, yeah, you can check that out on their YouTube page if you want to learn more about our project. And thank you.